Hey everybody, how's it going? Stoner Dave here. Now, I finished up the series on impedance, and while there's still a bit more that you could talk about as far as resistance and impedance, it's not that imperative as far as understanding electronics, right? You can do electronics with what I've shown you and be really far ahead of the curve as far as other people that know a little bit of electronics. But there's still quite a lot to cover. Now, for this next part, we're going to start talking about semiconductors. And oh my God, this is a huge block of information. I was thinking where to start. And I was like, well, probably start with these. Let's see if I can get you to focus on that. Come on, focus. I don't know. Well, maybe it won't focus. Oh well, I'll try it from another angle, but this is a diode. Diodes are really the backbone of all digital electronics and a lot of the analog as well. This little piece of, well, silicon, really. This little piece of silicon is responsible for so much, right? So let's just delve into it from the beginning. Now, there are a lot of different things you can look up that'll tell you about this stuff. And I'm going to do my best, but I'll be honest with you. I don't have, I don't have the time to animate a PowerPoint for you. I kind of wish I did, because other sites that I've seen these videos on, they have the animation, and I really feel inadequate without putting in that animation. But I think you'll get this without too much going in. So let me go ahead. I've got a little circuit here that I've been working on, but I'm going to go ahead and tear that out of here. And I'm going to put you in an overhead position so that you can see this stuff as I'm putting it together. Okay, so here we have a diode, and I went ahead and drew the schematic symbol of the diode. This little black line here is representing of the cathode side. This is the side that, when forward biased, will go towards the low potential side of the system. Now, diode is composed of two layers of semiconductor material. These semiconductors it's called doping, and what it does is it creates a layer. One side will have what's called holes, and the other side will have what's called carriers. In other words, the holes, it's got one less electron on each of its orbits, and the side with the carriers has one extra electron as its carriers. So this side has the extra electrons called the P side. This side has a bunch of holes called the N side. And in between them, it creates this little barrier called the PN junction. Can't make this shit up. It is what it is. And what happens is, if you put a positive potential over on this side and negative potential on this side, these excess charges, these excess electrons, are going to be pushed in this direction, and they'll have to have enough potential to get over this PN junction. Now, in a typical silicon diode like this, that potential is approximately 0.7 volts or 700 millivolts. And once that potential is reached, these charges flow quite easily through there. So what you'll get is, I'll show you on my tester. I'll run the junction through there. You'll be able to see what happens as the voltage goes up and what happens with the current, because it doesn't follow Ohm's law like you'd see with a resistor, where you get just a straight line going up. Instead, what'll happen is, Ohm's law with a resistor, you get straight increase in current with increase in voltage. So on this line here, we have the voltage, and on this side, we have the current. And since the resistance is stable and doesn't change, as we increase voltage, we increase the current in a linear fashion. Well, with the diode, we have the same thing here. We have the voltage and we have the current. Yeah, I know, I used the I instead of a C. So what happens is you put the voltage on and it doesn't do much until it hits that area about that 1.7 or about that 0.7 volts. And then it just shoots up almost straight up. Not quite as straight up as this. It'd actually be more like this. But right about here, we get 0.7 volts. And this increase in current just keeps going. Within a small voltage range, the current will shoot up exponentially. The reason why this is important is because everything under here, no current flows. So if you have one of these diodes put in the proper way, you can prevent a bunch of issues that you could get. Like, for example, you may see on a schematic, you'll see a diode going like this with the positive voltage here and negative voltage here. And the whole idea of this is that if you put the wrong polarity on there, the current will flow through this diode, protecting the rest of the circuit downstream from any reverse voltage damage that could occur. For example, if you've got, say, a voltage regulator, right? Let's see, I'll just do a simple voltage regulator like this, right? And you have, let's say, plus 10 volts, right? On this side. And you have a, say, 7806. You have 6 volts here. Simply putting a diode like this will prevent you from, and you have your ground right here. Prevent you from getting damaged if you, say, hook this up with 10 volts here and ground here. Right? Because this doesn't understand the whole concept of all of this. But this diode here, or a diode that's inside some of them like this, will cause this current to just go back here. And the only thing that gets damaged, this little diode, which can handle a pretty large amount of current. But it's essentially that, hey man, let's say you put the 10 volts here, ground here, and you're looking at getting the 6 volts here, right? Put it in backwards. That's the setup, right? This is the setup. And this diode here, because this essentially is going to your circuit. your circuit's over here, blah, blah, blah. But setting it up like this diode takes this current right to here. Nothing gets damaged. Little steps like that can be done quite easily. So that's the diode. Now there are a lot of different diodes. Now this just happens to be a switching diode. I believe this is a 1N 4841. So this is the basic diode, right? There are also Zener diodes. Rectifier diodes. Fun thing about the rectifier diodes, they're actually not any different than the switching diodes. Just the speed at which they change. It's called slew rate, but not really important at this point in time. There are Schottky diodes, which have a much lower forward voltage than these. Still really great at reverse voltage protection. In fact, Schottky diodes are often used to rip people off when they're trying to buy germanium diodes, because germanium diodes and Schottky diodes have really similar forward voltages. Another application for these, particularly these ones, which are the same as these, except for these will handle higher currents typically, is rectifier circuits, right? So let's take a look at your wall outlet voltage, right? Your wall outlet voltage is essentially a sine wave that looks like this. And it repeats this over and over again. It has an RMS value in America about 120 volts at 60 hertz. Hardly anything will run on this particular voltage. In fact, the only thing that I can think of offhand that could actually make use of this particular voltage is an incandescent light bulb. Incandescent light bulbs, they only need to have voltage going through them. They don't care about polarity. So the voltage constantly changing back and forth gets the filament hot, and the hot filament glows, and that's where your light comes from. And typically it'll glow at this voltage and this voltage respectively. This added voltage that it goes up to and down to, well, that's just making it so hot that when it goes through this transition here, it doesn't have enough time to cool down to where it doesn't have an illumination. Plus, at 60 cycles per second, you wouldn't be able to see that cool down anyways. But neither here nor there. Today, everything runs off of DC voltage. So what you get is you get something looks like this. Your AC source, I'll just put this down like that, showing you that the opposite side of it is a ground, and we're going up here. And you'll use a diode. So let's say we have the diode set like this. And now this output will look like this. Positive cycle here, the negative cycle, it won't pass through. So here's the zero voltage right here. This dotted line here equals 0.7 volts. Negative half cycle doesn't come through, but then the positive half comes through here. And you'll see that going on and on and on and on. Right? That's just it. So this is what's called a half-wave rectifier. One diode, and you get this. And it's called rectified because it's no longer alternating current, even though it's got the humps. It's a direct current because it's always positive. That's the difference between AC and DC, right? An AC current goes positive and negative. DC is always positive. But this isn't very good either, because if you see, if something's requiring a particular voltage here, during this time with right here, it's off. So you get something that's kind of blinking. So to rectify that, we put a capacitor in here, just like that. Now what happens is the capacitor gets charged and it starts to discharge. And it charges back up and it discharges. Charges back up and discharges. And this right here is what's typically called ripple voltage. The distance from here to here is ripple voltage. Now, this ripple voltage may not be acceptable for most applications. So how do we deal with that? Well, more diodes, obviously. So we're going to do what's called a full bridge rectifier, which is essentially we'll take our AC source here and we will put it into diodes. Make sure I draw this the right way. And let me think here. God, it's been so long since I've actually had to draw these out. I usually just draw a circle with a diode inside of it as a representative of this. I'm sure I have some copies of this schematic somewhere I can look at. I'll just look it up. I'm not doing this because I don't understand it. It's just because it's been so long since I've actually looked at it. Full bridge rectifier. Yeah. So this would actually... Oh, I did draw it wrong. See, nobody fucking tells me anything. Just joking. So we have the circuit going like this, and this ground side here. Technically it's not a ground. Connect here. Then what we get is on here, and I'll draw a little loop going like this. And we'll say this is going to be our ground side, and this will be our signal, right? So what we end up with here is something that looks like this. A little spread out more than that, but I'll draw it a little better. Something looks like this, right? And the way it works is the positive signal comes through this side, and as the positive side's going that way, the negative side's going this way, going down to ground. So positive half of the cycle, this diode here and this diode here are active, allowing current to flow through. The negative going to the ground, positive going out to the signal. Then during the negative side cycle of the diode, this diode here becomes active and this diode becomes active. So the positive voltage comes out this side and the negative voltage comes out this side. And you get this. Now again, look at the size of this ripple and it's just too big. So pop a capacitor right here. I just connect it to this ground here. I don't need to draw another ground signal here. Capacitor there, and you get the discharge like this. Typically we use a high value of capacitor so the charging time is such that we have minimal ripple voltage. And this, of course, we can see we've got ourselves a DC voltage, because this will look just like this on the output. Ripple voltage low enough that we can ignore it. And that's how your full bridge rectifier works. This is what's inside of these things. Well, it's more than just that. Really what you have is a transformer, which is two inductors close enough to each other that the magnetic flux in one inductor induces a current in the other. Primary gets an alternating voltage from the wall, which creates a magnetic flux, magnetic fields that rise and fall with the changing voltage. And this induces in this case, a smaller voltage of approximately 5 volts in the output coil. Pretty neat stuff. If you were paying attention to what I told you about inductors and magnetic fields, then you already know this, but that's okay. And of course, you've got your whatever circuit you're powering. So I'll just put a little arrow saying that this is going to the other circuit. And that's the basic diode. Now, I'd mentioned there was other diodes. I mentioned Schottky diodes. Schottky diodes would never be used for this because of the low forward voltage. And when you put reverse on them, they don't give the way that these do. So they're really fast and they adjust to the current really well, but they are more used for blocking than they are blocking a DC from going into reverse than they are for rectifying. They're not really used for switching because switching is, again, a different operation, right? All these different diodes, they all have their places, though. But the most famous of the different diodes, I would say, are these guys. The Zener diode. The Zener diode, very similar to the typical diode, which has a symbol like this. The Zener will have these little marks on it like that. And what's neat about the Zener is that they are put in reverse diode. That is, the cathode will go towards the positive and the anode will go towards the negative. Now, these guys are designed with a special purpose. It's something that's called the Zener voltage, or VZ. And these guys are often used in voltage regulators. See, what happens with these guys is they block the voltage completely, right? They block it just like any other diode until you reach this Zener voltage. When you reach this Zener voltage, this guy will start conducting. And I believe this is a 15 volt Zener. Let me just run it through my tool here. And I'll get the Zener voltage for you. See, I have a program that allows me to test any and all semiconductor up to 3 terminals. So this one is a 6.8 volt Zener diode. So what that means is that any voltage below 6.8 volts will flow right past here. So say we have a voltage source here, just put here, and this would be out, and this. So little arrow going through it like that says that it's variable, so we can adjust it, right? So anything 6.8 and below will go straight past this thing and be on the output. Once you get 6.8 volts or above, this will only output 6.8 volts, and all the other voltage will flow through here to ground. Now, there are other factors you have to consider, like how much current this Zener voltage can take and what its breakdown is going to be like, and all that thing. But funny enough, these things are used in voltage regulators because of how accurately they will hold this voltage in place. So you'll have transistors and other things set up in there to give you some kind of a constant current on there or whatever, constant voltage, help this thing regulate. But this thing right here, that's the key of the fucking voltage regulator, really. It's what holds it at its maximum voltage. Now I could show you how to design a fairly simple voltage regulator with these that will hold up quite well. Like, for example, if I wanted to create a 6-volt regulator, well, I could do that by putting a simple transistor like this and understanding the situation, right? So this is going to go to ground. This is going to have my Zener voltage here. And this will have my source, right? Should work. Have a voltage comes in here. No, wait, that's not right. No. That's not right. Let's see, we have, let me see it, draw it like that. So we have our V in and our V out, and that's what you're going to get. Right there, there's a positive voltage regulator, just like that. There's our ground as well. That's all it takes. So this 6.8 is our equals our VZ. Out here, we should be seeing approximately 6.1 volts. This VN won't really matter. It won't really matter because it's going to go through here just like it's supposed to. The forward voltage of this thing is about 0.7 volts. So the transistor will activate as soon as this voltage is applied. Activate. You'll get this voltage right here. Bada bing, bada boom. pretty simple stuff once you understand how these work. And you can put other circuitry in here. Definitely you're going to want capacitors hooked up. That kind of stuff. It's really simple to make. And there are a shit ton of other ways to make regulators, many of which are more stable than this. This guy, while it's nice and simple, it's not exactly the most stable. And you'll find that if you try it. What else? We talked about the PN junction, right? I talked about that, I'm pretty sure. Is there anything more to talk about with diodes? Well, yeah, obviously there's a shit ton more to talk about with diodes. But I think that would be something that would be a bit more advanced than what you'd want to talk about here. Oh, yeah. Resistors, right? You actually would have to have resistors for current control, right? You'll have to have a resistor here going to your ground and a resistor here going to your source. So I'll just draw that right here, and your battery, and we'll say it's variable. And this one will have to be a high impedance. And the reason why it needs to be a high impedance is because, well, you're setting the current limit for this thing, right? So if you don't have a high impedance on there, and this thing is just going essentially straight to ground, this thing is going to try to drive this thing's current as high as it can, right? It's going to try to drive it as high as it can. So you need to have the a high impedance here. Also, the load is going to be a part of that as well. And this right here, also current limiting. And the value should be a moderate level. Again, so you can set a reasonable current impedance. This is also to protect against no load conditions, because no load can be pretty vital to everything. But it's a real solid fucking circuit. Oh, I should probably put that so you can see what I drew. High impedance here, moderate impedance here, some voltage source here. And this is also going to determine your dropout voltage, which is an important thing to know about voltage regulators, because you have to have a certain voltage above what you're trying to get out in order to get a regulated voltage. So it brings about a question, right? What is a regulated voltage? What does a voltage regulator do? Well, to answer that question, you really need to know what an unregulated voltage source is. An unregulated voltage source is something like this, a battery, right? So why is it called an unregulated voltage source? Well, that answer is really quite simple. If you measured the voltage of a battery, I'm hoping that this battery is charged so that when I measure the voltage, you can see the full voltage, because it's supposed to be a 9-volt battery. So let's take a look at this 9-volt battery with no load on it. So connecting positive to the positive, negative to the negative. 7.18 volts. So it's not a fully charged battery. Kind of low. All right. Now, I'm going to take a resistor. I'm going to take hopefully a reasonably high resistor. 1K resistor. That's reasonably high. And I'm going to place this 1K resistor across the terminals like thus. Let's see, get that on there. So put it like that. Whoops. And I'm going to measure the voltage across the resistor. And connect the terminals. 6.82. Without the resistor, 7.11, 7.12. That's a 1K resistor. Reasonably large impedance, causing a significant loss in voltage. Why do you suppose that is? Well, unbeknownst to people like Detroit Wrecker, every voltage source has its own internal impedance. So, a fully charged 9-volt battery, which this is not, typically has about 9.3 volts without a load. And when given a 1K resistance, it will show 9 volts. And as you drop that resistance lower and lower, that voltage that you read also drops lower and lower until you get to a point where you don't see any voltage difference between the two terminals. And that is essentially when you've got such a low impedance, that's essentially a short. So, the question, why is there that drop in voltage from the open volt or the open source compared to the source with a load? Well, remember, every voltage source has its own internal impedance. So you put a resistance across the battery, you're creating a voltage divider with that internal impedance. Voltage divider means that that loss in voltage is dissipating across the internal impedance of the battery. Now, people that know electronics, they will tell you that this makes perfect sense. People that don't know electronics, they don't understand that stuff, and they will just assume that it's some voodoo witchcraft or something. I tried to explain this in a previous video a few years back. I was talking about this guy named Scott Grove. He's got a guitar channel on YouTube. Pretty successful channel. Gets a lot of content, a lot of views. And he made a video one time talking about guitar amplifiers and saying that you can double the power of your amplifier, or practically double it, by putting a smaller resistance speaker on there, smaller impedance speaker. He said that if you're using an 8 ohm amplifier and you put a 4 ohm speaker on it, you'll actually get like 1.7 times the power output. And he was justifying what he was saying by pointing at Ohm's law and the power formula of voltage times current equals power. Now, what he didn't seem to understand is that the power is actually the voltage across the impedance times the current through the impedance. And when you're looking at something like an amplifier feeding into a speaker, speaker's a pretty low impedance in general, and the amplifier has an impedance that's designed to match that. So if at 8 ohms you're getting 100 watts and you drop that to 4 ohms, and this 100 watts is the rating of the amplifier, right? These amplifiers are rated based on their maximum power output. Means that 100 watts is for a matched load. Well, you drop that load down in half, and you essentially are getting what we got with this battery when I put the resistance across it. The battery itself still has the same voltage coming through it, the same properties of the battery. The battery hasn't changed any at all. You just put a load on it. Now, with no load, you've got the most impedance you could possibly get. So you see the most voltage you can possibly get out of the battery. And in this case, it was 7.11 volts. You put the load across it, and you create the voltage divider with that internal resistance, and you get a little bit less than the full voltage. That's why it's called 9-volt battery with a 9.3 volts on it. You want to make sure you don't put too low of a resistance on a battery, because I'm going to get a 10 ohm resistor. This one I'm going to want to find a way to hold it in place without using my hands, because it's going to get pretty hot. Put this right here. This is a 10 ohm resistor. Now, if I measured the voltage across this, which I should probably set that up myself here, I'm going to do it an easier way. So I'm going to wrap the resistors, the legs of the resistor, around the probes of my voltmeter. So there we go, here and here, and wrap that there. Wrap this here. And that should be good. All right. Turn it to my ohms reading so you can see that we are dealing with, oh, this is a 1K resistor. I don't want 1K. I want 10 ohms. There we go. 11.1, that's pretty close to 10. So let's put this in our volt read and connect the terminals. See our voltage? Look at that. 2 point, and it's dropping so quickly. Look at how quickly it's dropping. You know why it's dropping so fast? This battery is discharging very quickly. Now, I'm not going to touch that resistor right now because it's pretty freaking warm. 7 volts going across 10 ohms. That's what? Let's look at our Ohm's law. Well, actually, it's only, what, 2 volts? 2 divided by 11.2. So, 170, about 179 milliamps times, we'll say about 2. So, a little over the quarter watt that this thing is meant to handle. But remember, without the resistance on there, you got 7 volts almost. Remember how it used to say 11 volts? That's how quickly the power drained. And it drains very fast as the battery is getting closer and closer to death. I mean, technically speaking, this is a dead battery because it's just that drained of its voltage. Because I've done this experiment with it a few times. But that, my friends, is why when Scott Grove tells you that you can get more power out of your amplifier by hooking up a small load to it, you can rest assured when I tell you he doesn't know what the fuck he's talking about. I am well schooled in electronic concepts. And what you just witnessed really is a aspect known as the maximum power transfer theorem. Typically, when you're using a battery, you're not looking for maximum power. You are looking for maximum efficiency. Now, what does that mean, maximum efficiency? Well, I have a very high impedance resistor here, 7.5 mega ohms. 7.5 mega ohms. I'll show it here again. Uh, 7.5. See that? All right. And we put that across these terminals and measure our voltage. 7.3. See that? I take the resistor off, doesn't even change. That all that voltage going across that resistor, and it stays the same voltage even with the resistor on there. That's maximum efficiency, high resistance on the load, high impedance on the load. However you want to talk about it, it doesn't fucking matter. Resistance, impedance, Ohm's law doesn't care. Ohm's law says they're the same. And that's the bottom line, because Ohm's law says so. All right, so unlike Detroit Wrecker and Scott Grove and other people that think they know what they're talking about when they talk about this stuff, I already know that there's a lot more to these things than what I'm talking about here. There is a lot more. So if you're not catching it all right now, don't worry. Don't feel bad. I'm only one person, and this is a very large, complicated subject. So in a 45-minute talk about things where I'm talking about something as simple as a rectifier diode and how they work, there's going to be some things I'm going to gloss over. Not because I don't know them, but because they're not necessarily that important to the concept. Important thing to understand about diode, right? Typical switching diodes and rectifier diodes, they will block voltage in one direction and allow it in another. And that's true of not only these diodes, but also these. This is a light emitting diode. Now, what's special about a light emitting diode is, well, I'll show you. Let me see here. I hook up positive side of my voltage. Hold on, let me get started here. I'm going to turn that down to 0. Hook up my negative side to the cathode. I'm going to slowly turn up the voltage, right? really slow. I'm at about half volts, 0.7, 0.8, 1.3, 1.5, 1.8, about 2 volts. Right there, you see it come on? Right there at about 2 volts, it starts coming on. 2.2 volts, and we start seeing light. Eventually, what's going to happen is this diode is going to burn out. Right there. 2.5 volts. So this diode, I just ruined it for your benefit. At 2.2 volts, it got 150 milliamps going through it, which is too much for this thing to handle. Typically what we would do with these is we would hook up some kind of a current limiting resistor that we can actually calculate using Ohm's law. So I'm going to do this again. This time I'm going to start with 9 volts. 9 volts, 9.0 volts. I know this because I've got my power supply right there. See it? 9 volts. And I'm going to do a little bit of a calculation to determine what size of resistor I should use for this diode. Now, to really do this, I've got to look at a few things. I got to look at the forward voltage of the diode and its maximum current rating. So I'm going to go to the data sheets and I'm going to look up this particular diode. It is a 5 millimeter red LED, and search. And we're searching. Here we go. All right. Absolute maximum value is 30 milliamps. So, forward voltage 2.1, and then we got the wavelength and all that shit. We don't really worry about that, but we need to look at what we're dealing with. So what we're going to take, so we're going to take the forward voltage, which is usually represented with a V with an F, and we're going to subtract that from the source. So let me write this down here better. We're going to take the voltage source, represented by Vs, minus the forward voltage, represented by Vf, and we're going to divide that by the current. Now again, 2.1 milliamps is the typical, right? But it doesn't really matter. We can be close to that. So I'm going to just look at this and we're going to go 9 minus the forward voltage, which is where is that? My forward current forward voltage 2.1, and we're going to divide that by our current. We're going to look for current. Reverse current. The maximum values. Okay. Well, our maximum is 30. We don't want to do the maximum, but we'll do 320. So this says our resistance that we're looking for is about 345 ohms. I do not have a 345 ohm resistor, but I do have a 390 ohm resistor. So we will use the 390 ohm resistor. Now, since I destroyed the first LED, I'm going to get another one very similar to it. So here's a red LED, and I'm just going to wrap this resistor here around the anode leg, which will connect to the positive, and this to the negative, and voila, got ourselves a nice red LED. And I can turn the voltage down, and it'll eventually turn off right there. 1.5 volts, it turns off. 1.9, 1.7, 1.8. 2 volts, it's on. Look at that. We're just actually just increasing the current going through there. And we go all the way up to 9 volts. Look at that. Nice and bright. We've got some leeway because we are at 390 ohms. But it works really good at 9 volts. Look at that. Nice and shiny little light. Now, that's kind of cool, right? That's your fucking LED, man. That's how you decide what to use for your current limiting resistor. Just take the voltage source that you're given, in this case 9 volts, minus our diode's voltage, which is in this case 2.1 volts, and we just divide it by the current that we're looking for. That's it. That's Ohm's law right there. And this will equal our LED, the resistor for the LED. Ooh, neat. And what's more, check this out. I can take this and reverse it, put it in backwards. No light, no current. It's completely blocked. Just like a diode's supposed to, it blocks the reverse current. Pretty cool. Put it on here. Light. Now, a lot of people don't know this, but this is also pretty cool. Solar panels. They induce electric current from light hitting them. They're actually made the same thing as these. The LED, when a light hits it of enough intensity, will generate a small electric current. Now, I'd need to take about 1 million of these and put them all together into something really small to generate any kind of a current that would be worthwhile, but it's still there and it's still kind of cool. All right, now I think I've covered everything about diodes. Can't think of anything else. Let me think. Yeah, LEDs, they come in all shapes and sizes. This is a 5 millimeter. These are 3 millimeter. I've got some really cool ones right here. These little guys are especially cool. Now, I'm going to, I'll just take this resistor. It's fine. Now, these guys, this LED is actually a little bit different than the red one. You'll see in just a moment why that is. And what'll be important to understand and why I have them. Get in there. All right, so here we go. Put the positive on here. Is that green? Now watch what happens when I take this and reverse them. Red. Now the reason I have these is I've designed a distortion pedal, well, overdrive pedal, using LEDs, and I was using two of them in the clipping element design. So just show you what clipping element looks like. Where's my pencil? Oh, how did I lose the pencil? It's just right here. Oh, I'll just use a pen. So a clipping element is an element that looks kind of like this. It's made up of two diodes. But they are reversed from each other. And they're set up in parallel like this. And the idea is that you have some kind of a alternating signal coming in like this. And the output will look like this, or something similar to it. Because what will happen is the signal at the top of here and down here are clipped off, because the positive cycle above this forward voltage will go through this diode to ground. The negative cycle, anything below this voltage, goes through this diode to ground. And everything in between just passes through. That's a clipping element. This is the part of the circuit that makes your distortion and overdrive pedals distort and sound overdriven. All right. So with that information, Detroit Record could actually maybe possibly think about considering designing himself a distortion or an overdrive pedal. But he says he already built two, and so far he's demonstrated zero. So go figure, right? So that mess of yammering and chatting and talking is everything that you have to know about diodes. At least I think. God, I hope I don't think of something else. Is there anything else I can think of? No? Not really. Not really. I would like to think that I'm going to get started on transistors next. But transistors are a world of fucking math and explanation and well, there's just a lot to them. And I just honestly don't think I could put all of that into a YouTube video. I can get you started on them, but I don't think I could finish them in any kind of a reasonable amount of time. I mean, look, we've already been talking for a fucking hour about fucking diodes. Diodes are fucking 100 times simpler than the simplest transistor. There's not a lot of math involved in a diode. I mean, this right here is all you need to know about finding your current limiting resistor. Bridge rectifiers, pretty well established right here. The only thing you'd really have to look at is what your voltage that you're trying to get, making sure that this is a large enough capacitor so that you don't blow it up from really just trying to charge and discharge it too much. An example, this capacitor right here, 4,700 microfarad for 35 volts. This is approximately reasonably good enough for like a 17 volt power supply. So you put in something like this right here, that would be reasonably effective for 17 volts. This right here, reasonably effective for 17 volts. Now, if you had to choose between the two, I would go with this one myself. Higher capacitance means that it's got a little bit more room on the plate. So you can handle running the current through there faster. Just means you can put more load on there. But this one will work fine. A lot of times we use these rectifiers to give us a positive and a negative voltage supply. And I'm not going to go into that because it's a little more complicated than what you'd be ready to deal with at this junction in time. But if your supply has got some kind of a tap on it, a center tap, you can set a center tap on your transformer. Well, I've got a transformer around here somewhere. Yeah, here we go. Here's a transformer that has a center tap on there right here. So you run this to your ground line, run these to your rectifiers, and all of a sudden this becomes a negative supply and this becomes a positive supply. And you'd actually have this being the negative supply going down like this, and run a capacitor here like that going to your ground, which would be going to your transformer, which is essentially this right here, blah, blah, blah. A lot of fucking explanation that would take me even more time to talk about, I don't think you want to hear it, so I don't want to talk about it in this video. But in future videos, I will discuss these different power supplies and how you go about designing them and what is the best way to go about getting a good, smooth, stable power supply. All right. So, after all that yammering and talking, I think I'm finally done. God, I hope I'm done. Yeah, I'm done. No. Am I done? Yeah, I think I'm done. Yeah, is there more to talk about? Is there anything more to talk about? No, not really. Not really. So, in the next video, I'll get started on transistors, and we'll start with the most basic, the bipolar junction transistors. Now, if you thought I was talking a lot in this video to cover this amount of data, the next video is going to be covering so much more. I don't even know if I'll be able to make it through the whole fucking thing. I mean, there's just so much that goes into a fucking transistor that the levels that you have to go through in explaining them, it's like just outrageous, man. Fucking, you can lose your mind talking about this stuff long enough, right? But I know people like Detroit Wrecker out there, they don't know this stuff and they want to talk about electronics. So talking about it for them will allow them to steal my concepts and make their own videos. And the guy's really trying to get monetized. I mean, he's really upset that he can't get monetized, but he doesn't want to take the responsibility that he just doesn't have anything interesting to say. He just doesn't have any way to engage new people with his channel. And he's upset that there are people out there that are able to do that. And I know I'm not one of them. I mean, fuck, man, my content sucks. Proof that my content sucks. Check out Electroboom's video on diodes. The guy is fucking way better at explaining this shit than I am. And he really gets to the heart of the matter really fucking quickly. So if you really want to learn about diodes and electronics, I recommend you go check out Electroboom. The guy's fucking hilarious. He's fucking super fucking smart. And yeah, he does things in his videos that make me kind of cringe, but I understand that he is actually being safe while he's doing this stuff, and he's just doing it for the comedic effect. He knows that there's going to be a spark, and he knows that if he really does it, he could get shocked pretty bad. And you'll see him do stuff, and it looks like he's getting hurt, but he's getting real mild shocks. You know, it's all fun and games until somebody loses an eye. So, again, watch Electroboom about this stuff. He's so much better than me at really everything that he does. And if you're wanting to learn this stuff, like really learn it, he's the guy to get you started on it. All right. Thanks for watching. If you made it this far, thanks. Have a great fucking day.